Lecture 5 is simply an overview of Assignment 1. So if you look at Assignment 1, you're basically going to have an introduction. What is the project about? So in this project, what we're going to be looking at is we're going to be looking at both deterministic and stochastic models. They're going to be for biological systems such as predator-prey, competition systems, and SIR model, which is the spread of disease. So we're going to have MATLAB program. The MATLAB program is what you're going to modify. The MATLAB program actually solves the stochastic differential equation using this method, and it gives what's called sample paths or realizations. So what you're going to actually do is you're going to run this program, you're going to look at the output, and you're going to answer some questions about the output. You're going to modify the program for a different system and look at the output. So basically in the competitions, so if we're talking about predator-prey, one of the species is the predator, another one's the prey. You're going to run the program for a specified period of time. If the prey dies off before that time, basically what it's going to do is consider the prey to be died off if the population reaches less than 1, which makes sense. You can't have half of a animal. So it'll basically say that the prey has died off if it reaches less than 1. It will calculate how long it took to actually die off, and then it'll run, I think in this case it runs 1,000 samples. So with that 1,000 samples, it calculates an estimate of how many times that species died off and what was the mean time to extinction. Okay, so an important note, do not get worried when you see this code. You do not have to understand what the code is doing right now. This is a really complicated code. The way it's written is really, it looks more complicated than what it is. We'll get into more coding later in the class, so don't go, oh no, this is the first assignment and this code looks horrible, I'm never going to be able to do this, I don't understand MATLAB. You have to change a few lines and that's it. That's all you have to do. You change a few lines, you run the code, and then you analyze the output. So the biggest thing that I want you to get out of this is to see the differences between deterministic and stochastic models. What is the differences between these two types of models? What is the result of adding randomness or stochasticity? How does that affect the results? So what you're going to see is with the deterministic, you may have one set of results. You may think, okay, the predator is going to win, the prey is going to die off. But when you add this randomness, then what you may see instead is that, well, the predator doesn't always win, maybe the prey wins sometimes. Or instead of living in perfect harmony all the time, maybe always somebody dies off. So you're going to end up seeing these differences between the two different models. And so what I'm looking for in this assignment is whether or not you can see the differences, whether you can analyze the differences, understand the models. So understand whether you're talking about a competition system, whether you're talking about predator-prey, whether you're talking about an epidemic, like a flu epidemic, or the spread of some type of virus. What does that mean? So if you interpret the results of the deterministic model and then the results of the stochastic model are different, then what kind of interpretation does that lead to? So explain the differences. So that's one of the main things that you're going to have to do on this assignment. Okay, so this is the system that is in the code. I'm going to just briefly go over this. The code is given as stochastic versus deterministic.m. Remember that .m. All of the MATLAB files are .m. Don't want to have, when you save it, so this is going to be a PDF file. You're going to copy, you're going to open up the script file, and you're going to save it. Save it as this name, but make sure you put the underscore. Okay, so the model that's in the system basically is a competition model, and there's a birth rate for species 1, a birth rate for species 2, a death rate for species 1, and a death rate for species 2. The model is basically given as the change of my species 1, change of y1 with respect to t, is given as the birth minus the death times how many are in my population 1. Here the change in my species 2 is again its birth rate minus its death rate times how many are in its species. So what you can see here is the constant terms and the birth and death give us these constant terms here. You're going to see, since it's a competition model, they're in competition with the other species, so that's where you have y1 interacting with y2. So you have this y1 times y2 term, so this is when they're interacting. And you also have they're in competition with each other, so maybe for food sources. They're competing against each other for food sources. Typically, the competition, you're less likely to compete with your own people, your own species. You kind of hopefully share a little bit more. But anyway, so then this is your competition with the other species. So you have some initial values. This is the deterministic model. Notice there's no randomness here. There's nothing added in. This is the corresponding stochastic differential equation model. So stochastic, SDE. This is our DE model. This is our SDE. So this is our stochastic model. Now we have this W1 and W2 introduced, which are, sorry for the typo here, this is an AND. So our independent Wiener processes. And again, you don't have to know how to get from one to the other. This will all be covered in the SDE section, the SDE module for this course. Well, I'll actually have you derive, probably even this one, at the end of the semester. So you will actually derive this, but for now I just want you to see the output. Okay, so solving the ODE, basically what does this method do? It takes the previous time step, so this y1k, how many species were at the previous time step, multiplies by the birth minus death rate, multiplies by some incremental step h, so here h is going to be small. For the stochastic part, it does the same thing. So you basically take the previous one. Here this eta is just going to be some kind of stochastic, it's going to actually, if you look in the code, it's a random number generator. So this is our stochastic process. This eta changes each time step. When our new value gets less than 1 for either one of these, then the time stops. Or if the time exceeds the maximum time, then it also stops. You're going to do this for, there's a variable called nsamp. You're going to do this for however many sample passes you want to do. So each time you're going to get a different realization. And then h is just, like I said, the time step. And the output I have here below. Okay, so this is what the output you're going to see in MATLAB. You're going to have deterministic output and stochastic output. Deterministic says this is I case 1, stochastic is I case 2, just to keep the two separated from each other. Here, deterministic, you only have one sample. Remember, there's only one output. You don't have any extra realizations. There is one and only one. There's nothing that's varying. So it is exactly 1. If you go over here, your sample, we're going to run it 1,000 times. So the initial code runs it 1,000 times. Our maximum time is 100. That's the same for both. And our time step is 0.1 for both. Okay, so what this shows is you have two different species. The species 1 and species 2. The TP1 corresponds to the time to extinction for species 1. And P1 corresponds to the probability of extinction. So remember, deterministic, you have one result only. So here, species 2 died off. And it died off when you reached about 87.1. When the time was 87.1, that's when the species died off. Over here, you run 1,000 simulations. What does this output say? This output says that 442 of those 1,000 simulations, species 1 died off. And here, 558 of the 1,000 simulations, species 2 died off. So here, species 2 died off more times than species 1 died off. So the probability of extinction is about 55.8 for species 2. Probability of extinction is about 44.2 for species 1. Notice that varies over here, right? So here it looks like species 1 always wins. here species 1 doesn't win all the time. Sometimes it dies off. And when it dies off much faster on average than species 2 dies off. So here on average it takes species 2 about 13.1 to die off, whatever time increments we're talking about. That's why I'm not saying what time increments. But 13.1, and over here, notice that in the deterministic case, it's a lot different. The time to death for species 2 is a lot longer than what the stochastic model is predicting on average. Okay, so this P3 here corresponds to if both species survived. And so here, P1 plus P2, it should be 1 in each case, assuming this is 0. If this is not 0, then you should have P1 plus P2 plus P3 should be equal to 1. And then this is the average time of either one dying off. Okay, you're also going to have some graphical output. So the first graph you're going to see is actually a plot of the deterministic versus stochastic. So here, this is our deterministic plot. The solid lines are deterministic. This is what happens to our species 1 as a function of time. Our species 2 as a function of time. These are two different realizations of our stochastic model. So one realization, your population 1 goes up, and then your population 1 goes up while your black one here goes down. And then the other one, your black goes up and the red one dies off. So this is an example where here the first one, the red survives, the black dies off. In the second simulation, the black survives and the red dies off. So then you're going to have one other graphical output. In the top you're going to have deterministic, the bottom you have stochastic. Sometimes it's nice to plot what's happening with population 2 as a function of population 1. So this is how they are changing with respect to each other. This is really just what we saw on the previous slide, our population with respect to time. Again, this is one simulation of population with respect to time. So in this case, our population 2 dies off and our population 1 doesn't. And this is what happens to each other as a function of time. So what happens to population 2 is a function of population 1. Okay, so you're going to be looking at 4 different models in this assignment. You're going to be looking at the system that I just talked about. You're going to be looking at another competition system, a predator-prey system where one of the species is a predator, the other species is the prey. And you're going to be looking at an SIS system, which is, you can think about it, it's just kind of like the flu spreading. So you have people that are susceptible to getting the flu, people that are infected to getting infected with the flu. You're infected and you interact with people who are susceptible, then what's likely to happen? Some of those are going to get sick. And then once you recover from the flu, actually this might be better to be a cold. And when you recover from the cold, you can actually get the cold again, so you go back to the susceptible category. There are the main lines to change in the code. You have 9 lines here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So some of the things that you're going to be asked to change are the sample times, how many times you run it, the maximum time you run it for, the number of time steps, your initial populations. So for your different systems, your birth rate and your death rate are going to change. Here, birth rate and death rate. These last 5 lines here, these lines will only be changed for the SIS model. So you only have to worry about these on that last model. And then, as always, with this assignment, with any assignment that you have, with the lectures, with comprehending anything that I've done in class, if you need help, please ask. Ask now, don't ask later. Ask before it's too late.